Hi everyone, my name is Alexandra Pierce. This is my Physics 2212 Lab 2. The purpose of this experiment is to further investigate the data obtained during Lab 1 by creating a more sophisticated computational model for calculating electric force and charge on the charge tape. We will model the tape as a line of charges instead of a point charge to account for the distribution of charges along the tape. As for the main results, we found that the magnitude of charge on one piece of tape is equal to 2.49 e to the negative eighth coulombs, which is more than 2 times higher than the magnitude of charge calculated using the point charge model from Lab 1. For the models, we're having an experimental model and a computational model. The experimental model will be the same one that we used in Lab 1, and we'll also use the same data. And then for the computational model, we're going to model the tape as a line of charges to compute electric force and charge. As for assumptions, we will assume that we can neglect air resistance. We will also assume that each U-tape has the same charge, and we will assume charge is evenly distributed throughout the piece of tape. For our fundamental principles, we first have Coulomb's law, which allows us to compute the electric force of one charged object on another charged object, like in the case of our charged tapes. Since we are working with distributed charges in this lab, we can use the principle of superposition, which allows us to approximate the net electric field as the sum of electric fields calculated for smaller pieces of the charged object. Gravitational force also comes into play because that is acting on the tape in the negative y direction. Newton's second law is also applicable because it tells us that when the momentum does not change, the net force on the object is zero, so all the forces must balance one another. So let's quickly recap the experimental model. For our system, we have the charge U-taped, and then our surroundings is everything else. For the initial conditions, we have that the electric charge on the tape is zero, and then for our process, we have that two pieces of U-tape were created by quickly pulling a piece of tape off the base, which will result in a charge on the U-tape. The U-tape is then determined to have a positive charge because it was attracted to a negatively charged pin. Tape B was hung by each end on two rulers, and when approached with tape A, tape B began to levitate due to the repulsion of positive charges on each tape. And the distance between tape A and tape B was measured. So here's that experimental data that we obtained from Lab 1, and we will then be plugging into our code for this lab. And then let's just quickly recap the Lab 1 results from the point charge computational model. And so we found that the magnitude of electric force / gravitational force was 2.11 e to the negative third newtons, and the magnitude of charge on one piece of tape was 1.06 e to the negative eighth coulombs. So here's our computation model. Here are some of the values that we obtained from our experimental model, and then here's the charge that we were able to determine on that piece of tape. And this was done through trial and error to see which value would give us equal magnitude of electric force and gravitational force. Then right here we have a function to compute the electric field, and then here we have a function that creates a line of charges for our computational model. So this line of code right here is done to divide our tape into small finite pieces to calculate the point charge of each of those pieces. Then we have a scale factor for our electrical field arrows and scale factors for our gravitational force and electrical force arrows. So these functions right here are done to calculate both the electric field and the electric force at each small finite piece of tape that we've created. And then we have the function right here that will then add these values onto the total to calculate our total electric force on the piece of tape. And then here's just some output values so we can see what the magnitude of the electrical force is and the magnitude of the gravitational force. Here's the output free body diagram from our code, and notice that the magnitude of the electric force and the magnitude of the gravitational force are equal, and that's because F net on the tape is equal to 0. And then here again is our magnitude of charge on one piece of tape that we determined through trial and error. So as for our comparisons between models, realistically the computational model and the real-life experiments still have discrepancies, even with this new improved computational model. Gravitational force and electric force are not exactly equal in real life, and other forces are likely acting on the charged tape. Dividing the tape into finite segments of point charges to determine the charge proved to be more accurate to real experimental conditions than the model that treated the tape as a single point charge. As for our sources of error, we have that the pieces of tape could have had different charges from one another. There also could have been mishandling of the tape, which could have resulted in charge discrepancies, and we did not account for other forces from the surroundings, like air resistance. So for that what if question, in Lab 1, we did treat the tapes as point charges, a single point charge, and we got that the charge was 1.0667 e to the negative eighth coulombs. In Lab 2, we treated it as a distribution of charges, and we got that the charge was 2.49 e to the negative eighth coulombs. The charge calculated in this lab is more than double the charge calculated in Lab 1, which highlights the significant difference in charge calculations between the two models. And then for that why question, the estimates differ because the first model oversimplifies what was happening in the experiment. The model in Lab 1 treated all the charges as if they were concentrated at one point, but really they were distributed throughout the whole surface of the tape. This was accounted for by the line charge computational model. Therefore, the charge calculated by the model in this experiment is likely closer to the real-world value because it's more accurately representing the distribution of charges on the tape. So for our conclusions, breaking the tape into smaller point charges was a more accurate way to compute charges, and then dividing the tape into infinitesimally small pieces to compute electric field would make the results even more accurate. And then point charge models do not appropriately reflect the charge distribution of macro scale objects. Thank you so much for watching.